Oh, okay. Hello, my name is Michael Chan.
My name is Vanche Chowdhury.
I'm Jonathan Tai.
And I'm Andrew Nagal, and for our final project for the computer vision course at WPI of fall 2017, we decided to do object detection and localization. So the problem we wanted to address was that in terms of industry, object localization is used prevalently, but is typically utilizing high-cost systems such as LiDAR for mapping for detection of objects, or complicated camera systems that involve multiple cameras in order to understand where an object is within a 3D space. Within the industry, when those sorts of technology are considered too costly, instead what they do is they hard code the locations of certain objects. For example, within warehouse industries, when ABB robots are used, typically the location of the objects they need to pick and place are hard-coded, and the positions of where the robot arm needs to go are hard-coded because it's fairly simple for them to execute. The problem with this is that since the locations are hard-coded and there's no extra degree of sensing, a lot of mistakes are bound to happen, and since there's no sensing method, those mistakes aren't caught on by the system itself, they're only caught on by a user. So in order to combat this problem, we decided to gear our project to provide a solution. So our goal for this project was to develop a low-cost object detection and localization method that can be used in multiple environments, i.e. multiple industry environments. So the advantages of our proposed setup is that we could have this rig in which a camera, such as the camera pictured on this slide, move along a single plane and take two images. With these two images, the XY position of an object can be determined. Since our rig would be portable, as seen in a later slide, it would also allow for a high degree of variability in different types of environments, i.e. different industry environments, or different scenes. So how we would do this, so in terms of our methodology, we would select an object we wanted to recognize, feed it into a trainer in order to determine what features are relevant of the object in order to recognize the object in different types of scenes or pictures. And then, as mentioned before, we would take two snapshots with our camera along the same plane in which the object would be in both snapshots. And we would use those images to detect the objects, and because there are two images taken with different angles, we would be able to determine the distance of that object from the camera itself.
So we utilized two methods of object recognition in our project. The first method was PCA analysis. Eigenfaces, of course, were then taken from a host of 1,200 mugs which came from an online source, and the top eigenfaces were then selected to, of course, then create the eigenspace projection, and which then gives us an image reconstruction of the most mug-like general image, the average mug, so to speak, that we could then use to compare with the scene in order to attain the mug and get the mug from the scene. Our second method was utilizing feature matching, which essentially had us take a template matching approach towards the problem, where we took one of our mugs and took an image of that mug and used that as a template in order to match the mug from the scene to our template mug, utilizing surf features similarly to how we did in our class. And these two methods we implemented on both sets of images that in our single scene that we have created. Now here you will see that is a reconstruction of our scene. As you can see, there is a rail atop which the camera slides, and there is a scene with a couple different mugs and two rubber ducks, a little egg, some tape, and a backpack in the background. As the camera is moved to the other side, once it reaches the end, an image is taken, and an image is taken on the beginning end as well. This allows us to achieve some binocular vision, which allows us to do some of the triangulation calculations we will get to later. Here is an example, actually the actual two images we ended up using in our calculations and our testing. As you can see, this provides a very clear, definite, different image towards each other, where one is clearly at a different rotational angle towards the mug than the other and has different elements in the scene as well.
So when using our principal component analysis with the mugs, we trained our algorithm on a set of images gathered from ImageNet of a set with 1,200 different images of mugs. Pictured here are our 6 top eigenfaces that we extracted from our mugs. As you can see, our results with PCA were inconsistent at best, with the mugs either being partially detected as shown in the first 2 images, or as shown in the second set, not detected at all.
Our other method of object detection was feature matching, and this was particularly a challenge with mugs because, as we can see in the image, mugs do not really have really strong distinguishable features. Over here, the mug is mostly showing the Halloween picture as the feature itself rather than the mug itself. And so in order to combat that, rather than just using features of a general mug, we decided to choose a specific mug, in this case, a WPI logo mug. And this provided us with much stronger features, and it was a lot easier to actually match the features onto the scene with this kind of mug. So in terms of the results for this process, we can see on the left of the slide that the feature matching does work really well, where it can match the WPI logo from the individual mug to the mug in the scene. And it can use that matching to determine the area that is covered that belongs to the mug. So as we can see on the right, it is a fairly big square, or a polygon rather, and so that can kind of lead to problems in the triangulation, as we'll see later. The red dot over there is also the centroid that it calculated. And yeah, so this is calculated for each of the images and then used later on in triangulation. So for triangulation itself, we use the formula shown on the screen right here, where F is the focal length, W is the width of the object in millimeters or whatever, D is the distance of the object from the camera, which is usually what we're trying to solve in this case, and P is the number of pixels of the object inside the scene image. And so when we use this equation, we solve for D in both images and then average them, and this is what our predicted distances were. As we can see, both test cases were a little low compared to the actual distance, and part of the reason for that could be our P being too big. As we can see earlier, our area was really big, so the width of the mug in pixels would be much larger, and so since P is much larger, D would have to decrease. And that could explain why the predicted distance was lower than the actual distance.
Overall, we concluded that mugs are very hard to distinguish with principal component analysis due to the fact that there are very little distinguished features of them. We found that feature matching is more accurate, but however, due to the area covered by the mug, it's pretty hard to actually accurately detect that.
So the results overall proved fairly successful, as shown throughout our presentation. So we feel that the application of a low-cost camera on a planar rig would be fairly feasible for the use of different environments, particularly industry environments where sensing is very necessary for to decrease the amount of error. And we feel that a similar method could be developed further and would be able to be well implemented into very relevant practices.
Thank you. If there are any questions, please post them in the comments below.